Hello, I'm Arthur and I'm presenting our work entitled Vector Field for Curve Tracking with Obstacle Avoidance to CDC22. Our work is inserted in autonomous robot navigation context, where the robot needs to move safely in a given environment filled with obstacles. This applies to many applications such as surveillance, inspection, search and rescue, among many others. And to achieve that, vector field strategies have been widely used. In this work, we present a vector field method to follow curves while allowing obstacle avoidance in a reactive approach. In fact, a previous work from our group proposed a vector field methodology for robot navigation in time-varying paths embedded in n-dimensional spaces. The field is obtained constructively with the use of the Euclidean distance function to the curve. Several characteristics and advantages of this approach are presented with formal proofs in that work, but the presence of obstacles was not considered. Now, in the present work, we extend this method by adding the consideration of obstacles that may be dynamic or static, and this is achieved by, first, adapting the original method to accomplish the task of circumnavigating obstacles instead of following curves, and then combining both behaviors to achieve a curve following with obstacle avoidance. We also present ROS-based computational simulations and real-world experiments with a wheeled robot and a UAV quadcopter. Let me propose a schedule for this presentation. First, we are reviewing the previously proposed vector field. Next, I'm showing the method to circumnavigate obstacles. Then I'm presenting the final collision-free vector field. And finally, we conclude. The previously proposed vector field is based on the simple integrated model, where we aim to make the system trajectories converge to and follow a given time-varying curve that has this parametric representation. So to achieve our goal, we propose a time vector field, let me call it curve field. The method to find it rely on the point in the curve that is closest to the system. And from there, we find the Euclidean distance vector that will make the robot converge to the curve and the tangent vector that will make the robot follow the curve. Next, we multiply the convergent and the circulatory components by weights, following the idea of prioritizing convergence over circulation if we are far away from the curve, and the opposite if we are close to the curve. So with that, we can compute two components of the curve field. The first one is a unit field that follows static curves, and the second is a feed-forward component to compensate the time variance that may exist. And finally, we add these two components, multiplying the first one by another again to achieve constant norm as a predefined parameter. Let me point some interesting features of this field. The trajectories of the system converge and follow the target curve, which was the main goal. There isn't stable or unstable equilibrium points. The field is robust to bounded additive disturbances. It is a path following control approach in opposed to trajectory tracking ones. And the vector field can't be obtained by a potential field since it induces a limit cycle. Now, the goal is to adapt the vector field method to accomplish the obstacle following task as exemplified in the figure. The system must follow the obstacle at a predefined distance lambda, and it must deal with generically shaped obstacles such as disjoint parts or sharp edges. Following the same idea of using the closest point to the curve, now we use the closest point in the obstacle set. And from there, we compute the Euclidean distance function to the obstacle and the Euclidean distance to the obstacle at a predefined lambda distance. To enter a discussion about the proposed method, let SO be the equidistant set to the obstacle at a fixed distance lambda. In the figure, we can see the definitions with the SO set in blue, the lambda distance here, the Euclidean distance vector as a red vector that goes from the closest point in the obstacle as a green dot to the system as a black dot if we would like to draw the Euclidean distance at a fixed distance lambda. It will be very similar to this red vector, but it will be originated from here. And in gray, of course, we have the obstacle. In this two-dimensional example, SO has dimension 1, and therefore it is equivalent to a path. To follow the obstacle in this case, you only have one possible direction, which makes 90 degrees with the Euclidean distance vector. Therefore, just by rotating this vector, we can compute the entire field. But in general, this might not always work. With 3 dimensions or more, SO is a hypersurface around the obstacle, and this leads to infinite possibilities to circulate it. Thus, our approach uses an auxiliary vector field, let me call it A, and we remove this field component in the direction of the Euclidean distance function, generating a tangent vector with 90 degrees with the Euclidean distance vector. In this figure below, we have an obstacle as a ball here, as a dark shape, and the SO set is this surface in blue. And as you can see, there are infinite possibilities of circulating this ball. So to find and to choose one, we use an auxiliary vector field, A, in red here, and we remove the component of this field in the direction of the Euclidean distance in blue here, generating then the tangent vector in green. This is in fact choosing one direction among the infinity directions around this plane. From there, the approach keeps following the curve field method. We find a unit field to follow static obstacles and the feed forward gain, and we sum them using a gain to the static field to assure constant norm. And thus we have the final field to follow obstacles. Let me call it obstacle field. In general, the approach to find the tangent component may lead this field to singularities or local minimum. Let me use this figure here. In left, in blue, we have two different auxiliary fields. The top one is a field always pointing to the right, and the bottom one is a circulating field. And the goal is to follow the same obstacle. So when using this auxiliary field, we generate the vector field at the right in red. So for the top case example where the auxiliary field A is only in one direction, we attempt to follow the obstacle in one direction at the top and in other direction at the bottom, leading to singularities or local minimum. But in the bottom example, we always try to circulate the obstacle in the same direction, and therefore the field here is singularity free and has no local minimum. So let's get back to the two-dimensional case where there's only one direction of following the obstacle. In this case, instead of using an auxiliary vector field, we can just rotate the Euclidean distance vector. So here we have a figure where the obstacle is in gray, the SO set is in blue at lambda distance from the obstacle. We have the robot here as this gray circle, and the robot has a range sensor, and it's sensing the closest point to the obstacle and computing the Euclidean vector to it in the local frame, only using local information. And only using this, you can compute the entire vector field. In this case, singularity free, and only using local information, with no need to global localization, for example. And thus, we get back to the figure from the start of this section that is actually a result in a stage-based simulation. We're using ROS, stage simulator, where for different values of lambda, the system was able to follow the obstacle, also dealing with sharp edges and disjoint parts. Here we have another example. Now it's a real robot experiment doing the same task of obstacle following. And it also deals with generic shaped obstacles. Now we want to show the final collision-free vector field where we combine the behaviors of following curves where we can and avoiding obstacle where is necessary. The first thing that we will do in this approach is inside the obstacle field, we will choose the auxiliary vector field as being the curve field. By doing this, we make the system follow the obstacle as close as possible to the curve. And the idea is to make the robot follow the curve when it's safe. By that, we mean the distance to the closest obstacle does not decrease when we follow the curve, and the obstacles are far away. It means by the distance to the obstacles is greater than a predefined threshold. But when there is an imminent collision, when we are very close to the obstacle, below another threshold smaller than the previous, and the distance to the obstacle decreases when we follow the curve, we try to circulate or circumnavigate the obstacles in order to reach its avoidance. And finally, to avoid abrupt transitions between these two fields, we have an intermediated state that is weighted by a scalar theta. And in this state, it's reached when the distance to the obstacle decreases when we follow the curve, but the distance to the obstacle is smaller than the first threshold, but greater than the second threshold. So going back to the figure, in the blue area here, we have the curve field activated, which is the first conditions. It is safe to follow the curve because the obstacles are far away, or if we keep following the curve, the distance to the obstacle does not decrease. In yellow are the regions that we have imminent collisions, which means that if we keep following the curve, the distance to the obstacle will decrease, and we are too close to it by the threshold. Finally, in green, we have the intermediate state, which is just a transition between two behaviors. To corroborate the theory with solid results, we have this vector field stack, which is a set of ROS packages that allows simulations using our vector field approach in different robot models, with the obstacle avoidance and using one of the examples from this set of simulations, the example where we have a UAV quadcopter, we have in the top figure a snapshot of the trajectory, and in the bottom figure we have this graph, where in blue is the distance to the curve, in red is the distance to the obstacle set, in yellow is the first threshold, and in green is the desired distance that we want to follow the obstacle, the lambda parameter. So at first we see that the system starts far away from the curve, around 4 meters to it, and it starts following the curve. So the distance to it is decreasing, and it converges to the curve. But at some point, an obstacle approaches the system, and its distance is below the threshold. This means that the system will have to move away from the curve in order to follow the obstacle and accomplish the avoidance. And we can also see that the following obstacle stage is at the distance that we predefined. After accomplishing the deviation from the obstacle, the system is allowed to get back to the curve. And this keeps happening. We also have this experiment where a wheeled robot is following a curve and obstacles are placed in its path. And the last result I'm going to show is this experiment where a low-cost UAV quadcopter, it's following an ellipsoid curve and deviating from this obstacle that I'm holding here. In this last experiment, this was the setup that we used in order to control the low-cost drone, where the localization was provided by a set of OptiTrack cameras. And the behavior of following the curve and avoiding obstacle with this graph is very similar to the previously showed UAV quadcopter simulation. To conclude, this work proposes a collision-free vector field, and we show ROS-based simulation and experiment to corroborate our theory. Our obstacle avoidance is a reactive circumnavigation approach. And to deal with the infinite possibilities direction to follow an obstacle, we propose an auxiliary vector field A. But for future works, we intend to elaborate more on this to always have a singularity-free obstacle vector field. But we already have a solution for the two-dimensional case where we just rotate the Euclidean distance vector generating singularity-free vector field. Thank you very much.